Okay, good morning, guys. This is part two of the notes for this week that you've completed. Just a screencast here, hopefully clarify any misconceptions. Earth seasons. What causes the Earth to have seasons? As you can see here, we live in an area where we have four distinct seasons, very similar to the photo down here. Many locations do not have these four distinct. Some have two, like Florida. They kind of call it summer and hot summer, um, even though there is four seasons. They don't see or they don't feel a big difference in temperature. And that's due to the tilt. So we have seasons because of the tilt of the Earth on its axis, and remember that is 23.5 degrees. The Earth is tilted, and if this was straight up and down, this is the actual axis here, drawn not like a 4-year-old. And this right here, this would be that 23.5 degrees. Okay, so that's our tilt. Now, what would happen if we're more tilted? Well, if we were more tilted, let's imagine the sun is right here for this one moment. If we were more tilted, that means when we are tilted away in the northern hemisphere, this is usually our winter. Okay, so when the Earth is in this lineup, the most direct sunlight hits the southern hemisphere. If we were more tilted, what would happen is certain locations in the southern hemisphere would be hotter, which means that the winter in the Earth would be colder. So if we had more tilt, what we would see is we would see more extreme seasons. The summer would be hotter for us, and the winter would be colder. If we were tilted less, this is more uniform. That means if the sun were right here, again, okay, if this were the sun, and if this were the earth, let's go to blue here, in all four locations, okay, if we were just not tilted at all, the sun's rays would hit us at the same intensity no matter what season we were in. Okay, these are the four seasons. We roughly see one every quarter as we revolve around the sun. And if you notice here, the sun's rays almost always would hit at the equator, which means that we wouldn't really see a changing temperature. So if it was less, we would see more average temps all year. We wouldn't see winter and fall. Everything might seem similar to fall. It really depends on what the exact tilt would be. So if we were more tilted, we would be more extreme. Hotter summers, colder winters. Less tilted, more average. We'd have mild temperatures all year round. Now, as you go through, I'm not going to spend most of the time of this video on these four positions, but I just want you to notice that summer solstice, we have two ideas, solstice and equinoxes. Solstice means different, okay? So this means different hours of day and night. That means they're not equal. We have about 15 hours of sunlight. Greatest angle of insolation is at 23.5 degrees north, Tropic of Cancer. So here's the equator here, and I know it's kind of small in this picture, but that's the equator. The sun's rays are actually most intense directly above them at what we call the Tropic of Cancer. Okay, there's a small little dashed line that you'll see on most globes, and below it is the Tropic of Capricorn. So most intense sun rays are in the northern hemisphere, directly at 23.5 degrees north. That's the closest to us through the course of the year, and therefore we have summer. Now, our equinox dates are fall and spring. Both of those we see equal day and night. Equinox equal. We also notice that it's at the equator. Okay, so in this case, it's very difficult to see because we actually want to see the other side of the Earth, but the sun's rays are most intense at the equator. equinox dates, the sun's rays are most intense at the equator, and we have equal day and night. So equinox is kind of nice to remember. Our second solstice date would be winter solstice, and again we are facing away from the sun. In this case, we're tilted now away. So the sun's rays are most intense in the southern hemisphere at the Tropic of Capricorn. That means that it is cooler in the northern hemisphere up here, and that's why it's our winter. Solstice means that it is unequal day and night. So in winter, we know we do not see a lot of daylight. We're probably at 9 hours, about 9 hours there. And then we go to our last equinox date, which is spring. As I mentioned, vernal equinox is just another term for spring. During all equinox dates, we can imagine, in this case, we can kind of see it. The sun's rays are most direct here at the equator. Both the northern and the southern hemisphere have equal amounts of sun insolation, meaning intensity of sun rays, which we kind of finish up on this portion of notes. So equinox, equal day and night, and equator. Okay. This is a good picture here. It kind of shows you what happens as we're tilted towards or away from the sun. So in this case is our winter. And if you notice here, the amount, the intensity and the amount of sun rays is higher here in the southern hemisphere. That's why it is summer when we're tilted away, and winter in the northern hemisphere. And 6 months after this, when, if you can imagine, the sun's maybe moving over to here, even though the sun doesn't move. Remember that. The sun never moves, Earth moves. Okay, but just for the sake of this picture, if the sun were over here, we could see that we would have the summer because this large portion here would be full of sun. Now, again, the sun doesn't move. Remember, we move around the sun, so the picture would be the same. There's a good video here if you click on it. It says it cannot play media right now, but when you load it up, you should be able to. Just goes over the seasons. I also copied it at the end here. So as you're reviewing through this stuff, remember that insolation, incoming solar radiation, just sunlight. Insolation means sunlight, guys. And here's what happens with the two major seasons. Green. Oh, yeah, go green. So most intense here for summer. We're tilted towards it. That means the most intense is actually right here. The shorter is more direct. Tropic of Cancer. And remember, we live at around 44 degrees north. A little bit less. But so we're really close to the 23.5 degree north, Tropic of Cancer, that the most intense sunlight is. We're closer to the heat source in this case, in terms of the most direct sunlight, so therefore it's hotter. Now remember, we talked about aphelion and perihelion, and in one of those cases we are closer to the sun, but that is not going to make it hotter. Okay, seasons are due to the tilt of the Earth, not our rotation and revolution. Okay, rotation gives us day and night, revolution gives us a year. 6 months later, we see that the most intense sunlight is now below the equator at what we call the Tropic of Capricorn. And again, we're up here. So now we're much further away than we are here in June. And that's why we have our seasons. Here's an example of that insolation. And you guys probably feel this during the day. Around noon, the sun is directly overhead. This is like being closer to the Tropic of Cancer or Tropic of Capricorn when that sun is that way. Most direct, most intense sun rays. As the sun travels down across the horizon throughout the course of the day, imagine this is around 4 p.m. All right, so we have two things. We have like noon. We'll say 1 p.m. because it always is a little hotter around 1 or 2. And then we have like 6 p.m. And I know the green's not showing up very well. I apologize for that, guys. But so we can see at 1 p.m. we have more direct sunlight. It's almost directly above our head. We have more intense heating. At 6 p.m., the angle is lower. It hits the surface on a large area, and that means it does not warm up as quickly. That is just like we were talking about here. Okay, that directly overhead is right here at the Tropic of Cancer. As you move further away, it's like that sun is moving lower on the horizon. If we look, the sun's rays are all directly intense on this point of the arrow. Look down at the bottom here. If you follow this arrow, the sun's rays are extended across this huge portion of the earth, spreading out the heat. So the closer you are to the most direct sunlight, where the sun is directly above your head, the more intense it is, the greater the heating, the greater angle of insolation directly above your head. Okay. Here's kind of an example, and this goes directly with this graph to the side. So the sun's as the angle of insolation increases, if we notice, it's going from 0, which would be the horizon here, to 90. Let's see, laser. There we go. To 90, it goes from here, from 0, less intense. It's increasing to 90. So on the graph, 45 would be about here. Okay, that's 0. We said 0 is right here. 90 is right here. So this would be 45. So we can kind of see this is flipped. When the sun is very low on the horizon, very little intensity. As it rises, as it jumps up to 45 degrees right here, we see those rays are coming down, we're starting to hit the earth. They take up a good amount of the space down here. They're warming it up, but not super intense. And then as we jump all the way up here to 90, which is when the sun is directly above our head, those sun rays are perpendicular. They're coming straight down at the object or whatever's on the surface, heating it up more rapidly. This is a good animation. I don't know if it's going to show on your Chromebooks, but I just want you to look right here at this one portion and watch as this jumps up to represent lower angles insolation. So at the equator, the sun is directly above your head. All of that is sunbeam is 1 square meter. Very intense. Now, as the rays start to travel, because the sun's going to hit this entire side of the earth that we see here, as a portion of those sun rays hit a little north, it is now spread out over 1.15. We only have about 87% of the original energy or the intensity that we had here at the equator. We go up a little further. Now we're only at 50% up here, and this is 2 square meters. This is similar, it's about 45. If we figure this is the equator, here's 90. This is probably around where we are. So 2 square meters. We're only getting 50% of the sunlight, the intensity that the equator is. So latitude plays a role as well in angle of insolation. Some information here, some nice pictures. Same idea here. My drawings are in there. I'll let you guys go through there. There are some videos here that really help show the visual there, and I would highly recommend opening them up and watching them as you complete through this. They're very short, guys, but why do we have different seasons? This talks about as we go through our revolutions and our rotations. For example, the tilt. Very good videos to help visually show that, so I do recommend you watch them. And then there's some practice questions here that you guys have in some of your Castle Learning and other assignments. So please reach out if you have questions. We have a couple more weeks left, so stay strong. All right, and we will be talking about the end of the year here shortly. But please make sure that you're using these makeup days to actually make up your work. Some of you owe me some work still, so let's get that in. Thank you.